Section 3.3, Power Functions and Polynomial Functions. In this section, you will learn how to identify power functions, also identify and behavior of power functions, identify polynomial functions, and identify the degree and leading coefficients of polynomial functions. We will be looking at a new class of functions in this section, and we call it as power functions. These are really useful for applications where quantities increase or decrease at a very fast rate. So what is a power function? It is a function that can be represented in the form of f of x is equal to kx to the power of p, where k and p are real numbers and k is known as the coefficient. And if you notice, our power function is only a single term. The key characteristic of a power function is that the variable is in the base, and that is that variable x. So let's have some examples here. Which of the following functions are power functions? So remember, f of x equal to kx to the p power, and it's a single term. The first one, f of x equal to 1. Yes, because you can write this as x raised to 0, x raised to 1, so that is a yes. X squared, yes. X cubed, yes. 1 over x is also a yes. You can rewrite this as x raised to negative 1. Still, the power is a real number. Same thing with that 1 over x squared. This is a power function. You can rewrite this as x raised to negative 2. Square root of x is a yes. The root, you can rewrite this as raised to 1/2. 1/2 is a real number. Same thing with x cube root of x. So this is equivalent to x raised to 1/3. Okay, so let's say cube root of x squared. This is the same thing as 2 raised to 2/3. So all of this is a yes. They are all power functions. Okay, how about the next example here? Is f of x equal to 2 raised to x a power function? Yes, that's correct. So it's not a power function. Why not? Because, look at this, the variable is an exponent. So remember, by the definition of a power function, f of x is equal to kx to the p. The variable is the base, but here x is in the exponent, so it is not a power function. Next example, which functions are power functions? F of x is equal to 2x squared times 4x cubed. We can simplify this. 2 times 4 is 8. X squared times x cubed. So just to recall, power of exponents, x raised to m times x raised to m is equal to, yes, we add the exponents. So 2 plus 3 is to the 5th power. So is this a power function? Yes. How about g of x? You have 3 terms here, so not a power function. How about h of x? Is also not a power function. Next, identifying the end behavior of power functions. All power functions increase or decrease very fast, no matter the size of the values of k or the power p. The way we say the mathematically is the end behavior tends toward either positive or negative infinity. So now infinity is just a concept, not an actual number, but the idea is helpful enough that we will use it extensively. So how to express an end behavior? So always think about what happens on the graph when you go to the left or when you go to the right. So by looking at this even power functions, the green graph is x squared. H of x is equal to x squared, and the blue is x to the fourth when you square x squared. So look at that. X to the 6 is this red one here. So these are all even power functions. Look at the power 2, 4, and 6. So what happens to the left and to the right? All of this to the left is, we know that to the left is negative infinity and to the right is positive infinity. So what happens to the end behavior if the graph, if we go to the left, look at the behavior of these graphs, all these three, it goes to infinity. How about if we go to the right? Yes, the graph goes to infinity also. So how do we write that? So we can have a left end behavior. So as x approaches left, so that is to the negative infinity, then we can say that our f of x is approaching, we go up, so that is positive infinity. The right end behavior as x approaches to the right, which is to the positive infinity, our f of x approaches, look at this graph, if you follow all these three graphs, it approaches also positive infinity. Okay, so those are for all even power functions. How about for all odd power functions? So these are examples like a cubic, which is the green graph, and also the blue, x to the 5th or x to the 7th. They're all odd power functions. So again, what happens on the graph as we go to the right and left? So we want to get a left and end behavior of this graph. Okay, so left end behavior for odd power functions. So as x approaches to the negative infinity, f of x approaches, so this graph, if you follow this, is to negative infinity. But the right end behavior, so as x approaches to the right, which is to the positive infinity, f of x approaches, if you follow this graph, it goes up, so that is to the positive infinity. Okay, so take note of these power functions when they are even and when they are odd. Okay, I hope you saw the pattern for those examples. So all odd power functions look like John Travolta in a Saturday Night Fever. So the best example is always think about a cubic, so like this, or like this, oops, or a negative, or like this. So this is an odd power function. How about even power functions? Look like smiles or frowns. So always think about, this is a smile and this is a frown. So this is even and this is odd. So let's take a look at the end behavior functions of some of our examples here. So positive constant when k is greater than 0. Even power, again, like what we discussed earlier, as x approaches negative infinity, f of x approaches positive infinity. As x approaches infinity, f of x approaches also positive infinity. Here, for odd power, as x approaches negative infinity, it approaches, f of x approaches positive infinity, and as x approaches infinity, there is something wrong here. This should be negative infinity. That's typographical error. Okay, so as x approaches infinity, x approaches positive infinity because this goes out. Look at this, the graph. So that should be positive infinity. Okay, for negative constant, when k is less than 0, now you have the frown here. Look at this graph. As x approaches negative infinity, that is, again, it should be, sorry, negative infinity, approaches negative infinity, and as x approaches positive infinity, it is also approaching negative infinity, because as you can see here, they're both going down and down, both negative infinity. The other one, for odd power, when k is less than 0, as x approaches negative infinity, this should be, goes up, so that should be positive. Why is this? There's an error here. Then as x approaches infinity, then yes, so that is approaching negative infinity, goes down. Okay, all right. Example 4, describe the end behavior of the graph f of x equal to negative x to the 9th power. So if you're going to sketch this, it's an odd and it's negative. So think about John Travolta. If it's positive, it looks like this. It's like an S. If it's negative, it's positive. If it's negative, it's like this. So negative, so it should look like this. Okay, so what's going to be the end behavior of this? So think the left and right end behavior. So here, as x approaches negative infinity, what do you think? F of x approaches, yes, goes up, so that is positive infinity. And then to the right, as x approaches positive infinity, f of x approaches, so if you follow this graph, it goes down, so that is negative infinity. All right. Next section, identifying polynomial functions. We'll move on from the single term power functions to what's called in general polynomial function. So earlier we talked about power function, and those are all single terms. Okay, next, polynomial function is a function that can be written in the form, this form, and this is called the general form of the polynomial function. Each a sub I is a coefficient and can be any real number. Take note of that. Each product ai x I is a term of a polynomial function. Some terminologies that you need to remember here: the an is called the leading coefficients. The highest power n is called the degree. So the highest power, the highest exponent. And altogether, an x to the nth power is what you call the leading term. So take note of all these three: leading coefficients, degree, and leading term. Okay, example 5, identify the degree, leading term, and leading coefficient of the following polynomial functions. So we have f of x, g of t, and h of p. So let's start with f of x. You want the degree, leading term, and leading coefficient. So here, degree is the highest exponent, which is 3. Yes. And what's next? Leading term is yes. So this with the highest degree, so that is the leading term, negative 4x cubed. And the leading coefficient is, since this is your leading term, definitely its numerical coefficient is negative 4. So that is for f of x. Next, for g of t, what is the degree? The highest power is, yes, to the 5th. So degree is 5. Leading term, so let's just use LT, is the one with the highest exponent, which is this highlighted 5t to the 5th. And leading coefficient, LC, is of course 5. Okay, next, h of p. So the degree is, just use d, sorry, I don't have space. Highest exponent is 3. And leading term is negative p cubed. And the leading coefficient is, be careful, this is, your leading term is negative p cubed, so meaning understood that there is a negative 1 here, negative 1 p cubed. So the leading coefficient is negative 1. Okay. Next, identifying end behavior of polynomial functions. Lastly, we can tell the end behavior of polynomial function by simply looking at the leading term. This is because the leading term dominates the behavior of the graph. Okay, so take note of that. The leading term dominates the end behavior of the graph. So that is what we're going to do for these next examples here. F of x given, identify the end behavior of the following polynomial functions. So again, end behavior. So given the first one, given f of x equal to f 5x to the fourth plus 2x cubed minus x minus 4. The leading term with the highest exponent, that's the degree, is 4. So the leading term is 5x to the fourth. And this is the graph of this function. So what is the end behavior of this? So as x approaches negative infinity, f of x approaches. So if you follow this graph, that is, yes, positive infinity. Then as x approaches infinity, f of x approaches also infinity. And here, f of x, the second one, negative 2x to the 6th minus x to the 5th plus 3x to the 4th plus x cubed. This is the leading term because the degree is 6. And this is the graph, and based on this graph, as x approaches to the negative infinity, this is continuous. F of x approaches negative infinity. Same thing here, as x approaches to positive infinity, and this is continuous going down. So that is f of x approaches negative infinity. So we're just going to write it down here. As x approaches negative infinity, f of x approaches negative infinity. As x approaches positive infinity, f of x approaches negative infinity. The third one, the leading term with the highest degree, highest x power, is 3x to the 5th. As x approaches negative infinity here, f of x approaches, yes, negative infinity. As x approaches positive infinity, f of x approaches, follow this graph, goes up, so that is positive infinity. And the last one, negative 6x cubed plus 7x squared plus 3x plus 1, leading term is negative 6x cubed. Highest power is 3. And look at this graph. These are the two end behaviors, this and this. Goes up, so meaning to the positive infinity, goes down to the negative infinity. So as we write our end behavior, so as x approaches negative infinity, f of x approaches infinity, and then as x approaches positive infinity, f of x approaches go down, so that is negative infinity. Okay, all right, let's have some lecture questions and to review the whole section. For the following exercises, identify the function as a power function, a polynomial function, or neither. So number 6, f of x equal to x to the 5th. Definitely f is, yes, it is a power function. About 7, x squared cubed, so meaning you can rewrite that as 2 times c is x to the 6. So yes, again, it is a power function. about 9. It is not a power function. No. And it is not also a polynomial function, so it's neither. And then 10, sorry, f of x equal to 2x times x plus 2, x minus 2 squared. F is a polynomial. Because you can multiply everything, and when you distribute this, and it will be a polynomial. Okay. Next, for the following exercise, graph the polynomial function using a calculator. Based on the graph, express the zeros and the n behavior. So, use a calculator. All you have to do is just enter this. If you use a graphing calculator, a TI calculator, or a Desmos, just enter x times x minus 3, x plus 3. So actually, you will see that you have 1, 2, 3, 1, 2, negative 3. You will actually see when you use a calculator that you have x, you have a point at 0, x minus 3, you have a point at 3, x plus 3, you have a point at negative 3. Meaning those are the zeros. And when you graph this, something like this. So the zeros are the points on the x-axis. Oops, sorry, it doesn't look good. The zeros are x is equal to 0, x is equal to negative 3, and x is equal to 3. Those points on the x-axis, they're x coordinates. And then the end behavior, go down and you go up. So as x approaches negative infinity, so that is to the left, f of x approaches negative infinity, this. And then as x approaches positive infinity, to the right, and if you follow the graph, it goes up. So f of x approaches positive infinity. Okay, so that's it. That is section 3.3. Thank you.